Hello, am I audible? For this presentation, we'll stick to equations of form 1 and del P del T equals LP, defined as minus divergence of mu P plus sigma squared by 2 Laplacian of P with an initial condition, and X is a d-dimensional vector, mu is a function from RD to RD, and sigma is a positive constant. And P is a probability density at all times. So closely related to this PD is this following E twice D, standard drift diffusion SD, dxt equals mu dt plus sigma dwt. And they are closely related because xt is distributed according to P at time t. Is it better? Oh, okay. So for ease of discussion, am I echoing? Okay. Okay. Yeah, I can. So for ease of discussion, let us classify the Fokker-Planck equations into two very broad categories. And category 1 is where mu can be expressed as minus grad V for some V. An example is a unit circle attractor, where mu is minus grad of x squared plus y squared minus 1 squared. And the other category, category 2, is where mu can't be expressed as a gradient of something. An example would be a scale 163 system with a butterfly attractor, where you have the usual parameters alpha, beta, rho, and there's the scaling s equals 100. The scaling makes sure that the attractor is contained inside a unit cube. And so we'll basically, as for examples, we'll just look at these two equations. And let's talk a little bit about the steady state. So recall the equation del P del T equals LP, which is minus divergence of mu P plus sigma squared by 2 Laplacian of P. So if a 0 of L exists, and which is also a probability density, we'll call it a steady state. So both of our examples admit a unique steady state, which will denote by P infinity. And let's look at how you can compute P infinity. For category 1, meaning mu is minus grad V for some V, you can write down the equation for log P like 5. And this has a very nice factorization. L log P, it factorizes like this, 2 terms. And when L has a unique steady state and mu can be written as minus grad V for some V, you can just make the second term go to 0. So make the second term 0, and it turns out that P infinity is just exponential minus 2v by sigma squared up to a normalization constant. So for category 1, you can analytically compute P infinity. For category 2, no analytical solutions are available in general, but pins or physics-informed neural nets work quite well in this case. And we can solve with pins, we actually solve the equation for log P infinity rather than P infinity in order to avoid the 0 solution. So there's an example of a pin solution computed with pin. So P infinity is unnecessarily computed with pin here because we know the true solutions anyway, but it's good for checking your setup or something. They look identical. So if you don't know about how pins work, you just take your favorite architecture, you apply the operator L or L log on it, and you evaluate it at some points sampled from your domain, you square it, sum it, and do a gradient descent with respect to the network parameter to get a decent solution. Yeah, so that's basically a very short description of how pins work. And usually you resample domain points after every few iterations. So this is where we didn't need to compute P infinity because we knew what P infinity was. But this is another case, category 2, where we actually don't know P infinity. And you can see that the pin solutions, they are quite similar to the solutions we get by simulation. And here the solutions are, this is a 3D in space equation, and solutions have been integrated in 1 dimension for easy visualization. And so, yeah, pins work quite well for computing P infinity. And so now let's talk about the time dependent solution. So even for the nice category 1 equations, no general methods exist for computing the time-dependent solution. But we can run Monte Carlo simulations. And sadly, pins are not very reliable for solving the time-dependent equation, since the loss or objective function for pin is not convex and they can have bad local minima, especially since P infinity also actually satisfies the time-dependent FP equation if you disregard the initial condition. And but we can get around this problem using the Feynman-Kac formula. So recall that equations of form 9, which is partial u partial t equals mu dot grad u minus qu plus sigma squared by 2 Laplacian of u with an initial condition can be solved using the Feynman-Kac formula given in 11, where u at time t at point x is the expected value of exponential integral minus 0 to t q xs ds times u naught xt, starting from x0 equals x. So basically, you're taking the expectation over this over the trajectories of the SD given in 12. We start, you generate paths of this SD and calculate the expectation. Paths of the SD till time t. But in order to apply Feynman-Kac, there are two requirements. Mu needs to be globally Lipschitz and Q needs to be lower bounded. The reason Q needs to be lower bounded is because otherwise this integral term won't behave nicely. And let's see. So we'll try to satisfy the requirements of Feynman-Kac. Let's talk about the lower boundedness of Q first. So the FP equation can be written in the mold of the Feynman-Kac formula, but it generally does not satisfy the two requirements of Feynman-Kac, namely the lower boundedness of Q, which in this case is divergence of mu, and the global Lipschitzness of mu. So, but instead of trying to solve for P, we can actually try to solve for H, where H is given in 13, where P is just H times P infinity. And H satisfies another differential equation, another PD, partial H partial T equals sigma squared grad log P infinity minus mu dot grad H plus sigma squared by 2 Laplacian of H. Now this equation of H fits into the mold of Feynman-Kac, so we get lucky. And we can actually try to solve 14 because we either know what P infinity is for the category 1 case, or we can actually compute it. So P infinity is known, that's why it becomes solvable. And note that in the H equation, the Q term is 0, so Q is 0 here. So you get a much simplified version of the formula 11. Yeah, so this makes more sense to use Feynman-Kac for H rather than P. So one down, one to go. So the other requirement is global Lipschitzness of mu. So you can imagine two Fokker-Planck equations with the corresponding SDs differing only in mu. Nothing else is different in these two sets, system L with mu equals mu L and system R with mu equals mu R. Everything is same, P naught is same, sigma is same. Basically everything is same except for the mu. And if you assume these following conditions, so assume the following are true. There's a compact convex set D plus where mu L and mu R agree. There's a convex compact subset of D plus, which we'll call D, such that if XL or XR, these processes start inside D, they stay inside D plus till time big T with probability greater than or equal to 1 minus epsilon. And the last one is support of P naught, the initial condition is contained in D. So under these assumptions, you can prove that if the solutions PL and PR exist, then their absolute difference integrated over D is bounded by 4 epsilon for all times from 0 to big T. And since our attractors, since our examples have attractors, the category 1 has the circle as attractor, category 2 has a butterfly attractor in the example. with the proper choice of D and D plus, we can actually ensure that there's D trajectories after starting in D, do not leave D plus with probability almost equal to 1 for all times, which actually implies that epsilon is almost equal to 0 and PL is almost equal to PR at all times inside D. So what it means is that the SD trajectories, they are attracted to, of course, the attractors, and they are reluctant to leave a compact domain that compact domain.
Pinak, you have 5 minutes.
Okay, thank you. So in other words, the existence of attractors in our examples allows us to solve for PR instead of PL, or replace a non-globally Lipschitz mu with a globally Lipschitz one without changing the solution in a compact domain, since all the dynamics occur inside a compact region. Yeah, so this is an example of solution computed with P infinity plus FK method, and this is a simulation solution for category 1 example at time 0.5. So what do I mean by P infinity plus FK method? Very briefly, modular a lot of tiny details. It's just you compute P infinity, either no P infinity or actually can compute P infinity with pins. And then after computing P infinity, you solve the solution, solve for H, and then you recombine H and P infinity to get the actual probability. So there's a 2D equation, so there's a heat map. And this is a solution for category 2 example at time 0.1. By already time 0.1, you can see some nice structures appearing. And again, this is a 3D in space. So one of the dimension has been integrated out for easier visualization. So the P infinity plus FK method, it matches the simulation. And yeah, so if you would like to play around with pins, I have some collab notebooks, and my Git repo for Fokker-Planck solvers is available here. And thank you for listening.
Thank you, Pinak. Now is the time for questions.
Could you briefly tell us how pins work?
Yeah, sure. So what you do is, so you have this equation, right? And for the log of P, you have this equation. So what you do, I'll use the, I'll try to solve this equation rather than this equation with pins. And the way to do it is you take a neural net, and it depends whatever your favorite architecture is. This is the parameters of the network. These are the arguments, space arguments. So because we're solving for P infinity, you don't need to worry about time. So this will be approximated as e to the something like this, and L log n theta x. So this x you sample, so you're solving, suppose you're solving this problem on a domain D, you sample your xi's from this domain, you plug it in, you compute this object, you square it, then you sum over the domain points, how many, maybe you take endpoints, and then what you do is this object, you can calculate the derivative with respect to theta and do a gradient descent on it. And the optimal theta will give you the solution.
Got it. Got it. Thank you.
I think we can take one more question.
Yes, I didn't follow completely. So you said that if mu L and mu R are equal on a particular domain,
yeah,
then you said the solutions stay very close for some time t. So the solution of the Fokker-Planck or of the Langevin equation?
The Fokker-Planck equation.
For what initial condition?
So inside, I said that they remain close inside a domain D, not everywhere.
So, but the initial, like the probability distribution has support outside D also, right?
The probability, there's an assumption that P naught had support in D.
Only in D. Oh, okay, fine. And then
but numerically, it's easy to, if you have a Gaussian that's outside D, it is almost 0. mass, then it's not really.
Yeah, if it's okay, right? Yeah. Okay.
Okay, so let us all thank Pinak for his wonderful talk.